Okay, so this week we're going to look at quadratic graphs in the real world and try to figure out what they mean. And to do that, you're going to look at their key attributes. Okay, so we're going to look at graphs, and then we're going to look at some equations. And there is a key attribute, the zeros, the x-intercepts, that you're going to be able to find from the equation, but that's next week, at least, lesson. So when push comes to shove, we're going to just go to Desmos and graph it, okay? All right, so let's see. These are the two teaks we're working on. A1A, all these ones are process standards. It's all that work we did at the beginning of the year, think like a mathematician. So what we're going to work on is applying mathematics, quadratic functions, to problems arising in everyday life or society or your workplace. Quadratic functions really are everywhere, and you can use them to answer a whole lot of different questions about what's going on. All right, and then A7A is the key attributes one, and I really kind of just shortened that down because we're just you need to be able to find the key attributes because that's what's going to let you answer the questions. That's what you're going to be interpreting. All right, so our learning targets. What you should be able to do by the time we're all done is graph the quadratic equation. Now, last week we talked about finding the vertex or the axis of symmetry, so you can find the vertex, the y-intercept, and reflecting, which is fine. And then, of course, we can always just graph it in Desmos as well. Okay, finding the key attributes of a quadratic function using either a graph or the equation. Graphs we worked on 2-3 weeks ago now, maybe, and the equations is what we were working on last week. And then, of course, kind of like the big one here is using those key attributes to answer questions. Do you know what the vertex of the function means in the real world for a real object that's been thrown or whatever? Okay, so I found this graphic last summer or the year before, and it kind of gives you the key attributes like we talked about before. But if you look, it tells you right here what they are. So the vertex tells you, the x value of the vertex tells you the maximum, when the object is at its maximum height. The y value tells you what the maximum height is, because the y value gives you the maximum. So that says how far, like if this was a rocket or a paper airplane or a soccer ball or anything really that you throw into the air will make a parabola. It will arc at some way, somehow. Okay, and then it comes down because of gravity. Okay, and the formula, interestingly enough, that they use for most of these motion along a path starts with negative 16t squared. And that is because of the acceleration due to gravity, so it always has that in there somehow. Okay, anyhow, so the y-intercept is how high it is when we start. So this one goes, but if it just starts at the y-intercept, so you're like standing on a building or you're holding the ball before you throw it, it's not on the ground. If the y-intercept is 0, that's going to be like on the ground. Anything else is it's being held, or you're standing on a building and throwing off, something, or you're maybe standing on a cliff with one of those, what do they call them, like a parachute, like gliders, and you're going to jump off the cliff. You're not going to go straight. There's going to be an arc there because, gravity, because science. Okay? All right, and then you have the zeros. The zeros tell you when you start. Now, if this 0 here is negative in the real world, that is probably not going to be, we don't care about that. It doesn't have a real application because usually, not always, but usually on the x-axis is time. We can't have negative time. So that's usually a solution for the function that models the situation, but not valid in context of the situation. Okay, and so then the other 0 is going to be when the object hits the ground, and then you can also tell how long it's been in the air at that point as well. Okay, and so then any point along here, how high is the object after however many seconds, that's going to be a point on that graph. And so you just put that x value into the equation to get the y value. Okay, now if I don't have a graph, and for whatever reason I don't want to make one, you know how to do this from the equation from last week. The y-intercept is where x is 0, so just put a 0 in there, or if it's in standard form, it's the c. Then you can find your axis of symmetry by that equation, opposite b divided by the product of 2 and a. That gets you the x value of the vertex, which you then can use to get the y value of the vertex. Okay, and like I said, there is a way to get the zeros, the x-intercepts, but we're going to talk about that a little bit later. But I think we can still do this interpretation right here. All right, then in looking for decent pictures of graphs or trying to graph them in Desmos so that you could see the numbers, I found this graphic. It says the same thing, it's just like colorful and drawn, and the only other thing this has is it dotted in that axis of symmetry there. But you see the x value is the time of maximum height, the y value is the maximum height, and it just has a couple more labels on here. So I thought you might like that one because it's all colorful and whatnot, so I included it. All right, so here's an example. This, I was trying to find a problem about a fire hose I had seen written somewhere, but I could not find a decent picture of a fire hose spraying water in an arc. But I did find this, and this, I have learned, is called a water salute. It's an airport tradition to honor military veterans, foreign dignitaries, or new airline service. So they get like 2 fire trucks on either side of the airplane, and then they spray water in an arc, and so then the arcs, intersect over top of the plane. Then I read sometimes they have 3, and that makes a triangle, and when you take geometry, you will know that where they intersect is a special kind of point and has properties and all that. Okay, so I thought that was interesting. So here we have a fire hose path. So we have a graph, and I'm basically going to go through here and answer these questions. This is not a whole lot of know how to explain this. It's a lot of kind of just reading a graph. So yes, they're the key attributes, but if you're like, oh great, I didn't understand those and now she's wanting me to do those again. Really and truly, if you can just read this graph, I think you'll be okay. So, how far above the ground is the hose being held? So that's going to be my y-intercept, okay, because here's time 0, okay? So this is the distance, the height, and, this would be the ground here, right? So it's right here. So I think we can say 375 centimeters, which actually I did check, it's about 12 feet. So that would be, I think, reasonable for a ladder truck if they extend the ladder. So you might want to say, no, it's not right on 375. I think it's 376, or, okay, they go by 25s. So you might want to say like 400. I'm going to just go ahead and say 375 centimeters. Okay, what is the maximum height of the water? Well, how high does this get? Well, right here, right? And that's right under 500, and it's in between 475 and 500, so maybe 480 feet. Or you could even say just under 500 feet, and that would be okay also, as long as you write the words in there. Okay, how many seconds... After how many seconds is the maximum height reached? Well, that's right in between here. That's our axis of symmetry right there, right? So, let's see. These go by 1, 2, 3, 4, by 1. So 1, 2, between 2 and 3. So 2.5 seconds. Okay, how long until the water reaches the ground? Well, from here where it starts to here where it ends is 5, 6, 7, 8 seconds. How long was the water at most 375 feet above the ground? So at most, so 375 or less. So I'm gonna get a different color here so I don't get confused on my graph. So at 375 or less, well, at all of this time, it's 375 and above. This is 375 and less. So it's from 5 to 8 seconds. So 3 seconds. Or you could write from, my C's are coming out all crazy. You could write from, 5 seconds to 8 seconds. Okay, what is a reasonable domain? Okay, domain and range. Okay, I'm going to not erase everything because it won't erase. Okay. So reasonable domain. Now I could write the equation for this graph, And then if I had just any parabola, any quadratic function, the domain is all real numbers. But that's not true here because I don't have I have 0 seconds. I don't have negative seconds. And pretty much after 8 seconds, it's done. The water is on the ground. So to make it go on forever is kind of pointless. So I'm going with where my graph starts, where my graph ends, and that's from 0 to 8. So I'm going to write, see if this shows up. I'm going to write 0 less than or equal to x less than or equal to 8, because I do have data at 0 seconds and I have data at 8 seconds, but not after that, because the water is just kind of pooling on the ground, maybe soaking into the ground, but it's not a parabola at that point. Okay, and so now range, we're going to go here. This is just like, I mean, you know, I probably could have went and found a graph that asked you about the range back, like from that first benchmark, honestly. I didn't think about that. I could just give you this graph and say, what's the domain and what's the range? Okay, and it's the same thing. So my range is 0 to like 480. So you can do this a couple ways. You can say 0, 480. Okay, so whatever you put here is going to be this number here. Okay, and but if you're saying, yeah, well, you don't know it's exactly 380, maybe it's 382 or whatever, you want to get super technical, then you can just write, okay, I know it can be equal to 0, but I just know it has to be less than 500. So you can do that without the equal sign. Okay, I think that would be acceptable as well. Okay, all right, so another example. So a soccer ball. So the path a soccer ball travels as it's kicked from the ground is also a parabola. It will arc up, reach a maximum point, and then come back down because gravity. Okay. So here is an equation this time instead of a graph. Okay, so I can answer these questions because I can find things like the y-intercept, the vertex, which will give me the maximum point, and how the axis of symmetry, rather, which will give me the vertex, which gives me the maximum point. Okay, so I'm going to go ahead and find those, but then I think there is a question in here I left in here that I'm going to need to go do my graph. Okay, all right, so just to review how to find the vertex. Well, A here equals -2, B is 14, and C is 0. So how high did I ask? No. I thought maybe it asked how high was the ball, where did it start? Well, it started at on the ground. Okay, so I know my parabola is going to look like this, and I know it's going to be concave down because of that negative sign. Sorry, it just dawned on me my dogs are playing in the background, so I kicked them out. I'm so sorry. I don't even hear them half the time. Okay, so there's that. So with the maximum height, and how long did it take, those kinds of things I can do by finding the axis of symmetry. So remember, that is the opposite of B over 2A. So the opposite of B is 14, -14 rather, and then 2 times -2. So that is going to give me, how much fun is this, -14 over -4, which gives me 7 over 2, which is 3.5, okay? So at 3.5 seconds, it's at its maximum height. So, did I ask that? What is maximum, when did the ball reach its maximum height? 3.5 seconds. And how high was that? Well, you're gonna put 3.5 in for t. And I know I said x equals t equals. Hey, notice here, I left this like this and forgot to mention it. That tells me what my independent and dependent variables are. That's time as a height as a function of time. Okay, so there you go. Anyhow, tx doesn't matter. I'm going to put 3.5 in for that, squared plus 14 times 3.5, and I'm going to grab my calculator here. and do that. And I get 24.5. So that means that the soccer ball was, well, sorry, I forgot to put in seconds and feet, 24.5 feet. Okay. How high off the ground was the ball at 3 seconds? Oh, well, it has to be less than 24.5, right? Because 3.5 was 24.5. So now I'm just going to take this 3 and put it in here instead of 3.5. Okay, so I'm going to have negative 2 times 3 squared plus 14 times 3. And that is going to give me, let's see, negative 2 times 9, negative 18, and 14 times 3 is 42, minus 18, 24. Okay, so 24 feet at 3 seconds, 24.5 feet. So it's traveling pretty much a foot a second, right? In half a second, it went another half a foot. Okay, but that's a question for much later, the velocity. That's a much later, not an Algebra 1 question. Okay, after it reached its maximum height, how long did it take to drop to the earth? Okay, so that's the one, the maximum height is the vertex, which is where the axis of symmetry is. So therefore, that should divide the graph in half, okay? And for how long the ball was in the air, again, we could solve that, but you don't have that skill yet. So I think now let's go to Desmos and graph this. We'll check the reasonableness of the answers that we have, and we'll use our graph to answer the rest of these. To here, how long did it take to drop to the earth? Well, 3.5 seconds. Okay. And how long was the ball in the air? Let's go. So 7 seconds. And now let's talk about reasonable domain and range. The ball was in the air for 7 seconds. So that makes our domain from 0 up to and including 7. Because after 7 seconds, the ball's just laying there on the ground. Like nothing happens. Okay. What is a reasonable range? Well, the ball starts on the ground, so 0. And then returns to the ground, so still 0. And then the highest point is at 24.5, so less than or equal to 24.5, because it can't go any higher than that. Okay, so that's just like when we were doing key attributes, you would have said the range is y is less than or equal to 24.5, but we're not going, like this soccer ball isn't getting drilled into the ground, so there are no negative values for y, so we're cutting it off at 0. Okay, so this is all well and good. You know how to do this, so that was a little bit of a review, but in the end, you can just put it in Desmos and get your answers that way. There's nothing wrong with that. Okay, I'm going to add a Desmos graph, and I'm going to graph in here negative 2, and I'm just going to use x squared, but you could do t squared if you wanted to. I think it will still work. Negative 2x squared plus 14x. Oh, it does that to me all the time. 14x. Okay, so now let me see if I can move my graph so I can see all the pieces here. All right, so I see I start at 0, and I can see that all these little minor grid lines go by 1. So 1, 2, 3, 4, 5. So at 3 seconds, or 3.5 seconds, I guess, is where that is our maximum point right there. And if I look over here, it is at 24 right there, or 24.5, because that's a little bit higher than 24. It's kind of hard, my pen is thick. Okay, so that seems reasonable. Okay, so how long did it take then to reach the ground? Well, if it took 3.5 seconds to reach its maximum, then it should take 1, 2, 3.5, because I'm halfway between there, 3.5 to reach the ground, because it's symmetrical on that axis of symmetry. Okay, and how do I know that? Well, I just counted. How to make this? Oh, that's a little easier. So I just counted. Let me see if I can draw these things in here better. Drew in my axis of symmetry. We see that it's right here. Oh no, what's closed? I'm not sure. I got some sort of notice that something was going to close, so hopefully we don't have to start again. So this is my vertex right here, and so my axis of symmetry is right here, and I know I'm a little crooked. So 1, 2, 3.5, and then I have a half, 1, 2, 3. So 3.5 until it reaches the ground here. Okay, so let me go back for that. Well, from 0 seconds to 5, 6, 7 seconds. So it looks like 7 seconds. Yeah, that makes sense. All right, so that screen. All right, so now one more. We have a diver. The path of a diver is also a parabola, only it kind of goes the other way, opens up. The diver dives into the water, goes down in an arc, reaches the lowest point, and then comes back up and touches the surface, okay? So this one I did a graph for. I think this is pretty accurate, at least some sort of diver. Okay, so we have distance and time, and you see we're negative because we are diving into the water. Underneath the sea level would be 0, or the level of the pool would be 0. Okay, so how far above the ground is the diver's platform? Well, we see here the y-intercept is at 1, so he's starting 1 foot above, 12 inches. That seemed reasonable to me. I don't know. So 1 foot. Okay. How long does it take for the diver to reach the surface? So he dives in and he's coming out here and he reaches the surface in between 7 and 8. So we could say, well, it's more than 7.5. So you can estimate that. I'm going to say about 8 seconds. Because it's not exact, it's more than half, so I'm just going to go ahead and estimate about 8 seconds. Now, we will talk next week. There's a way you can tell exactly what that point is, that 0. Super fun, but we'll do that next week or maybe even the week after. We'll see how it goes. Okay. At what point was the diver the deepest? Okay, so this was a hard question for me to write because I wanted you to focus on the minimum point, but it seemed weird to say minimum depth because this seems like a maximum depth to me, which is the minimum point, you know what I'm saying? So at what point were they the deepest? It's right here, right? That's where the axis of symmetry comes in, that's the vertex, and that's right there at 7 feet. So at what point? I guess we could do time, 4 seconds, and he was 7 feet deep. Okay, depending on how you interpret that question. And like I said, it was hard for me to make that question make sense. I couldn't think of what I was trying to ask you. Okay, what is a reasonable domain? Well, again, we don't have negative time, so we start at 0. Even though you see our graph up here keeps going, because this is a parabola, I graphed it in Desmos, and I didn't put any restrictions. You can restrict the domain, and then that's where you get those endpoints. There's something I did last week that I made it have endpoints. But I didn't for this one because the path of this diver is a quadratic function that is defined at any value of x, but it's just not a reasonable domain. Reasonable is we start at 0 and then we go to 8. Because after that, unless he's then jumping up and down on a springboard or something, he's on the ground. So there's no need for time to keep going while he's standing there, right? So we're going to say 0 less than or equal to x, and I'm just going to say less than 8. Okay, that's reasonable. It can't be 8 necessarily. If you say less than or equal to 8, not a big deal in my opinion. So he's standing there for a fraction of a second while the time runs out. Not a big deal. Okay. What is a reasonable range? Well, he starts here at 1. And he goes as far as -7. So -7 less than or equal to y less than or equal to 1. Okay, 1 is his maximum height, because here he is on his little diving platform. There he is, getting ready to dive into the water. Okay, for how many seconds was the diver at least 3 feet under the water? Well, we go to where 3 feet under the water is, and it's from here to here. So that looks like 1, 2, 3, 4, 5, 6 seconds. Okay. All right, so there you go. We're just basically reading the graph. Look and pay attention to your labels. They're important, so you know where to be looking for the answers to your questions. And then don't let this domain and range. I know it's been kind of a struggle all year for some of you with domain and range. Reasonable is what makes sense. Does it make sense to have negative time? Of course not. It has to start at 0. Does it make sense to have this range go all the way to infinity? Well, no, because he's not like he's going to be on top of a 927-foot building and dive, right? Okay, all right, so just read the graph, and if they give you an equation, I know the paper we would do if we were in class has an equation on there. I don't know if I'll give it to you or not. We'll see. You'll have to wait, because I haven't done that part of the lesson yet. Go to Desmos and graph it, and then things should work out easier for you. Okay, I think that's it. Yes, just my credits and whatnot.